Take it away.
Do you see me and hear me well there?
Yes, everything's very clear.
Oh, okay, perfect. Well, so hi everyone. My name is Jacksen. I'm a master's student at Macquarie University in Newfoundland in Canada. And today I'm gonna talk about the magnetorotational instability in global disk simulations using the SPH method. I have been working in this project with my supervisor, Dr. Terence Trick. So first, let me start explaining how MRI works with this simplified sketch. We have an accretion disk around a central object, and there we consider two fluid elements at the same distance from the central object and connected by a magnetic line. So if we insert a radial perturbation on the elements such that one of the elements gets closer to the central object, then due to the differential rotation, the inner object will move faster than the outer object, and so the two fluid elements will move apart. So here, the magnetic tension will resist that separation and will slow down the inner object and speed up the outer object. So the role of the magnetic tension is to mediate the transport of angular momentum. And finally, the inner element will move closer to the central object, and the outer element will move to an orbit farther from the central object. So this is the generation of accretion due to magnetorotational instability. And it's important because it's one of the main sources of accretion disk. And regarding numerical studies of this instability, most of the work so far has been done with mesh codes using both global and local models, for example, with sharing box approximations. Here I just share some examples like using Pluto and Athena++. So our question is, can SPH simulate MRI? Well, to date, there have been just a few three-dimensional SPH simulations, but all of them use sharing box approximations. In particular, we've seen 2022 sustained MRI turbulence for at least 100 orbits using a sharing box approximation and with a modified SPH scheme. So our goal is to move from local simulations to the global disk and study the suitability of SPH to simulate MRI. So the previous year, when I presented the initial stages of my project in the Phantom Workshop 2025, the main problem that we had is the dissipation of magnetic energy. As you can see here, after just like 3 outer orbits, most of the magnetic fields were dissipated from the disk. So now, after 1 year of work, I'm finally happy to tell you that we could reproduce magnetic turbulence and sustain the magnetic fields for several orbits. So how do we get to this point? First, let me start with the disk model that we use and the initial conditions. So for this, we simulate a thin accretion disk, and at the beginning, we only use hydrodynamics to like smooth the profiles of the density, as you can observe here. And then we introduce a toroidal magnetic field with a constant plasma beta equal to 25. We use a locally isothermal equation of a state with different resolutions from 20 million particles to 100 million particles, and also different dissipation parameters. And well, the simulations are still running, so I'm just gonna present some part of the 60 million particle simulation. So, well, another difference with respect to 1 year ago is that we modified the SPH scheme to include the geometric density formulation in the magnetic terms. This is because in previous local simulations, standard SPH developed like these strong magnetic fields, especially in low density regions of the disk, as is the case of here, the corona of the disk, which are not observed in GDSPH. So because of this, we just decided to move ahead with GDSPH. And well, how well do we resolve MRI? Based on previous grid code simulations, we know that we need at least 6 cells per MRI wavelength to activate MRI. Now, to talk about convergence, we need more than 20 cells. And to compare this with our simulations, for the case of the 60 million particles, in the midplane regions and in the other regions of the disk, we have a resolution of like 30 smoothing lengths per MRI wavelength. And in the corona of the disk, like from 2 to 3 scale heights, we have like more than 10 smoothing lengths per wavelength. So with this, at least we should be able to activate MRI. And indeed, if we see the evolution of the disk, here the density and the magnetic energy density, we observe the production of magnetic turbulence. First in the inner regions of the disk and then in the outer regions. And at around like 4 or 5 outer orbits, we observe that the full disk becomes unstable, becomes turbulent. We can also observe this in the magnetic field components. Here I show the toroidal magnetic field, and here the radial magnetic field. As I mentioned at the beginning, we only had toroidal magnetic field, but after just the first few orbits, there is this generation of turbulent radial magnetic field, first in the inner regions, then in the outer regions of the disk, and the same with the perturbation of the toroidal magnetic field. Something that we are still studying, like trying to understand, is the origin of these strong toroidal magnetic fields in the inner region of the disk. It's not only in our simulations, but also previous studies have also observed the formation of these strong toroidal magnetic fields. It's probably due to the poor resolvability of MRI, maybe. Well, we are still studying, so I'm not sure about that. Well, now how do we convert or relate the magnetic turbulence with the transport of angular momentum? For that, we use this volume average Maxwell stress normalized by the magnetic pressure, which it basically quantifies the angular momentum transport due to magnetic fields. We observe first that it reaches like a maximum around 4 or 5 outer orbits, and it increases with the resolution. For the case of 60 and 100 million particles, it reaches values around 0.3, 0.35 that are in very good agreement with previous local simulations using SPH, but also with global disk simulations using grid codes like 0.4, 0.35. So yeah, we got like similar levels in the Maxwell stress. Another characteristic feature in the magnetohydrodynamic instability is the dynamo effect. So here I show the cross-section rendering of the magnetic fields. This is the toroidal magnetic field. This is the radial magnetic field. So to calculate the mean magnetic fields, we average over the azimuthal direction at a constant radius. In this case, I take the radius as 5 astronomical units. And here you see the evolution of those mean magnetic fields versus time. Yep, here it is. So the first thing that we observe is the generation of the boloidal magnetic fields after just a few orbits. Like here at the beginning, there was only toroidal magnetic field, but after like 5 local orbits, there is this generation of radial magnetic fields, and also the generation of reversals in the orientation of the magnetic fields that first originate in the midplane and then propagate to the atmosphere of the disk. Okay, so now, aside of modifying and taking different resolutions, we also modify the dissipation parameters. And here I'm going to introduce this Prandtl number, which corresponds to the ratio of the viscous dissipation to the magnetic dissipation, which in the case of SPH, we can calculate exactly, as is the case of artificial resistivity, related to this input alpha parameter, the signal velocity, and the smoothing length. So what we did is modify the alpha parameter that will correspond to different values of the Prandtl number. And as you see here, for the case of 40 million particles, we got that the lower the alpha parameter is, the higher the Prandtl number and the Maxwell stress are. And if we compare this with local simulations from Wiesent that corresponds to these little green circles, we got like very similar values and relations. So another agreement with respect to local simulations. Now, if we compare like the evolution of the magnetic turbulence with respect to the Prandtl number, we observe that here I'm showing snapshots of the magnetic turbulence. The turbulent component of the toroidal magnetic field. So we see that for Prandtl numbers lower than 1.6, there is not that much magnetic turbulence, especially here in the corona of the disk. But for Prandtl numbers larger than 0.5, like 0.6, 2.3, most of the magnetic field here is turbulent, the toroidal magnetic field, which also agrees with general results from grid code simulations. Now, what about the standard SPH? Well, all the simulations that we run using different resolutions, dissipation parameters, initial conditions with hydrodynamic initial conditions, Monte Carlo initial conditions, all of them had the same final, like the same end. The magnetic energy is being dissipated from the system, as you can see also here in the snapshots of the magnetic energy density, which is not the case for GDSPH. Even in low resolution simulations, we run a set of 1, 2, and 5 million particle simulations. And well, we cannot like resolve MRI properly there. We only have like 10 smoothing lengths per wavelength. So we are not resolving MRI properly, but at least the magnetic energy is not being dissipated as in the case of a standard SPH. So as I mentioned, we didn't solve MRI properly in that case. So the butterfly diagram is not that clear, but well, the magnetic energy is not being dissipated. Now, what's next? Well, I didn't present this in these results in this presentation because the simulations with Shamrock are still running, but we are also running high resolution simulations with 100 million particles. So I'd like to thank Jonah and the Shamrock team here for their support with the MHD module. So I expect to have more results in the future. And with that, I'm gonna leave just here this summary slide with the main results that we got and also some future work. So yeah, I'm happy to take any questions you may have, and thank you very much for your attention.
I know.
I mean, Jackson, just to say congratulations, first of all, like it looks amazing. So
thank you.
You seem to have made a lot of progress in the last year. I guess the main question, which you kind of answered already, is about this GD SPH stuff, which has been a strong claim from this other group. So in one of their papers, I made them check what change was really making a difference in the equations. It's not a big change. It's just changing the weighting of your neighbors. And it seemed to be only really needed to be changed in the induction equation that it really made a difference. So I was wondering what you mean when you said you tried GD-SPH. Have you messed up all the equations or just changed the induction equation?
Yeah, exactly. Because there is like, if we compare GD-SPH with the standard SPH into the standard hydrodynamic test, there is not like much difference. So because of that, we only change the magnetic terms in the MHD equations. Well, just the induction equation and the momentum equation. So for example, here I have the part of the induction equation, or this is a standard SPH, and this is with GD-SPH. It's just a small change, just modifying the weighting of the particles in the density gradient.
Yeah.
So yeah, we modify this only in the induction equation and the momentum equation.
Do you have any kind of feeling for why this makes such a big difference? I still don't really understand why such a small change makes such a big difference.
Yeah, I'm actually in the same situation. It's just a small change, but as you observe here, yeah, the difference is very like dramatic at the end. So not sure, maybe because of surface conditions in the disk where the density is like low.
Yeah, so is it to do with the fact the MRI gets going in the upper layers or something, and there's some interaction between the midplane and the upper layers that's kind of important? Or it would be much harder to resolve maybe in the standard formulation?
Yeah, probably. Well, because in the case of the standard MHD test, GDSPH basically produces the same results as a standard SPH, but with maybe lower resolution. But this is not the case here with MRI because we try with the same resolutions for both formulations, but the standard SPH always ended up with the dissipation of magnetic fields. So maybe it's because of the shear of this system. Yeah, I'm not completely sure.
Any other questions? I have a question, Jackson. I may be testing your knowledge and my ignorance at the same time. I don't understand. So when you have the MRI, you get a lot of turbulent different components of the magnetic field, but you have shown that you also get organized ones when you get these nice little rings, right? So, you know, organized fields are always nice because they can do things. And I'm doing binary interactions where fields may develop in similar ways. So what is the difference? Why does some regions of the disk get so turbulent and so disorganized and others are so neat?
Oh, you mean like here?
Yeah, like you had in one of the pictures. Yes, that's it. Yeah.
Yeah, actually that's one of the problems that we have observed, not only in these simulations, but also in previous SPH works, that they observe these strong, like kind of laminar magnetic fields in the inner region of the disk that are not observed, for example, in global simulations with grid codes. So could be because of the resolvability of MRI. If you see here in this plot, in those regions, like we don't have enough resolutions to solve the MRI. So maybe because of that, because of aggression in that region of the disk. Not sure.
It could be numerical.
Yeah. We expect, we think that it is just numerical artifacts because when we increase the resolution also, for example, for 20, 40, 60, and 100 million particles, we observe that these regions like decreases a little bit with the resolution. So it could be just a numerical artifact. But yeah, to say that, like, to conclude that we need like higher resolutions.
Tim has a question. Hold on, where is it? So back? No, Tim has a question online. So if you're online, just keep.
Oh, yeah. We're wonderful. Like, this is very nice. And I was wondering a bit if you've managed to do a bit of local test, as in kind of local box and that kind of stuff, like to try to fish out if the GE case is indeed like linked to the. I mean, if the improvement is linked to the case of the shear, because it's clearly like one thing that is kind of like destroying a lot of quality in the result in when I do local tests, especially in sharing box.
Yeah, short answer, we didn't. We test GDSPH, the implementation of GDSPH and standard SPH with other standard MHD tests, but not with local sharing box models. That would be a nice test to do, like, because we just modify some part of the MHD equations, not all of the terms. So maybe try with local simulations and see if we can observe like a more different results with respect to standard SPH. That's yeah, maybe we can do that in the future.
There is also the implementation of the sharing box in Shamrock. I don't know for Phantom, but there is one in Shamrock.
Oh, is it already implemented there?
Yeah, the sharing box with the sharing periodic boundary condition, they are already in.
Yep, great. So yeah, probably we'll do that in the future. That would be a nice test to do.